started. And we're going to hear this nice talk on stability and list replicability for agnostic learning.
Let's see, is this working? That'll get there. All right, yeah, hello everyone. My name's Ari Blondell. This is a joint work with my good friend Sean Gao, my supervisor Hamid Hatami, and his brother Puya Hatami. Yeah, so let's just jump right in. So this is stability and list replicability for agnostic learners, otherwise titled online learnability is equivalent to L epsilon list replicability. We'll go over kind of those terms and show you what I mean by that. So the setting is the classic binary pack learning setting. In the realizable case, of course, this means that we want to output some hypothesis with a low population loss, so below epsilon. However, we're mostly going to be talking about the agnostic case. In the agnostic case, in fact, we actually just want to output a hypothesis with population loss comparable to the best population loss in our concept class. Great. So the goal is replicability. In general, in sciences, in kind of a lot of things you do, we'd like to be able to do the same thing over and over again and get the same results back at the end. And so this is kind of the general idea of replicability in learning, is if you run the experiment over and over again, so you take a whole bunch of new samples and you put it through the same learning rule, you know, maybe you should be able to get the same hypothesis out at the end. So we want here, say H1 is equal to H2 is equal to H3 is equal to H4. Now, only fools repeat the same things over and over, expecting to obtain different results, which begs the question, are we fools? And I'll strive to try to answer that. To talk about this replicability, there's a few definitions. So here, realizable global stability is the existence of one hypothesis that is output with greater than 0 probability. And then the issue with this is that there are these hypothesis classes that kind of are unstable for all possible measures of instability. So for every row, there is some class that is not stable with global stability rho. So can we get rho close to 1? No. Great. So in order to fix this, Chase Murrah and Yehudayev came up with the idea of list replicability, which is to say that instead of just getting one good hypothesis that we're trying to replicate, we instead try to replicate from a big bag of hypotheses, or a list. And list replicability is simply the smallest list size such that this is in fact possible. And they came up with a great theorem and a great way of kind of reconciling these ideas, and that this is the maximum stability for a single hypothesis class is 1 over the minimum list replicability number. And yeah, so these are equivalent kind of notions. List replicability is much better because it actually retains some notion of pack learning. So this begs the question, what about the agnostic case? In general, kind of before this, if you look at a Littlestone dimension, so things that are characterized by Littlestone dimension, these are things that are equivalent in the realizable and the agnostic case. So such as online learning. Online learning is characterized by Littlestone dimension in the realizable and agnostic case. So is differentially private learning. So why not list replicability? And the answer is that it is in fact not. And so this came out last year, and it says that basically any concept class H is agnostically list replicable if and only if it is finite. Now a finite concept class for our cases is generally not something that's particularly useful. So we'd want to get better. What now? Well, their idea was basically to take this and loosen the definition a little bit to give it a little bit more leeway. So they proposed two possible relaxations. One of them was, what if the distribution that we are working with was restricted such that the population loss was less than some alpha? We showed that basically agnostic global stability reduces to this setting. So this doesn't offer us any more power whatsoever. The second relaxation that they asked was, what if the size of the list could in fact scale with epsilon? So as you get, as your error kind of gets smaller and smaller, as you get more and more precise, you might need a larger list to take care of that. And we show that that's actually exactly what they were looking for. In that this L epsilon list replicability, where the size of the list can scale with the error value, is possible exactly when the Littlestone dimension is finite. Great. And then I'm just going to spend the rest of my time doing a small proof sketch of one direction of our last proof. So here, what we're going to prove is that if the Littlestone dimension of H is infinite, then in fact H is not L of epsilon list replicable. So of course we first start off by assuming a list replicable learner, and we assume that the Littlestone dimension is infinite. This means also that the threshold dimension is infinite. This basically means that you can embed an arbitrarily large threshold into threshold class into our concept class. And then we, and I'm going to glaze over the details here, apply the Ramsey hypergraph theorem to restrict to a large subset X of our domain with some very, very nice properties. And the property that we're looking for, in fact, is that the prediction that our algorithm gives on a specific point, so after it is learned with its n sample points, is determined solely by the position of this new point x in relation to the other sample points, and the labels that the sample points were given in the first place. So here we can see these two sample sets are kind of very different within x. However, because of this, because of the way that we've restricted to this x, they should have about the same expected value when we run our algorithm and try to predict them. Right, so now on this x we're going to apply a uniform distribution and basically say that the points from the median to the left are going to be labeled with 0, the points from the median to the right are going to be labeled with 1. We can see that because this is in fact, as we assumed, a list replicable learner, it is a pack learner. So points on the left should probably be labeled with 0 most of the time, points on the right with 1 most of the time. And this means that somewhere in the middle, we must get some probability jump of about n over 2. And this probability jump, as I said, occurs actually at is going to occur at one of the sample points for any given sample. Yeah, and this is just because the expectations are given by the position within the sample set. So we have this probability jump, and what we do then is we use a so since our list size is finite, this means basically that we can approximate we can approximate the expectation of a point we can approximate the expectation of our estimation of a point by one of a finite set of functions, all of which are convex combinations of the members of the list. And this just leaves us with one simple task, which is to find two samples that overlap. So specifically where they have an empty point, they have a point x that they overlap on, one before the expectation jump that we identified, one after the expectation jump that we identified. Since they're both approximated by the same function, this shows that the expected values of x should be the same with those, which is a direct contradiction to the probability jump. And that's a contradiction, and that is the end of the proof sketch. Thank you very much. Any questions?
Can you comment on the other direction? Like, what do you pick L of epsilon to be? Like, sort of, what is the fundamental a thing that you gain by picking L as a function of epsilon? Like, can you comment a little bit on that?
Yeah, for sure. So the thing that you gain by letting L scale with epsilon is, and fundamentally the other direction is very easy in the sense of what we do, and there are of course many better methods to do this that give better constants, give better scaling, is we just kind of assume and we condition on the fact, we condition on the sample set that we draw being realizable. And so this actually is, right, so say if our loss is bounded above by 3/4, this has a probability of occurring of 4 to the n being our sample size based on epsilon. So because of this, we can kind of condition, because we let our list scale with epsilon, it can also scale with the sample size. And so this is kind of the power that we gain.
If there are no more questions, let's thank the speaker again. Really nice talk. And as the second speaker is coming up to the stage, there are some people that have come in. First of all, there are plenty of seats over here if people actually want to sit there. And second of all, if any speakers have entered the room and have not yet sent their slides to this email, it would be great if you would do that. So thanks. Let's listen to Omar talk about beyond worst case online classification. Thanks.
Hello. So I'll talk about joint work with Abhishek Shetty here in the audience and Nikita Zhivitovsky also at the conference. So let's start by recalling okay, so the setting of online learning. So we have an instance space X, a binary function class H. We proceed in T rounds. In each round, the adversary chooses an instance in the domain, presents it to the learner, then the learner makes a prediction, either +1 or -1. And after that, the adversary reveals the true label. And the goal in this setting for the learner is to minimize regret relative to the best function in the class. So mathematically, we just want to minimize the number of mistakes made by the learner relative to the best we can achieve using class H, and this is what we denote by opt. Now we have a complete characterization for online learning. Namely, a class is online learnable if and only if the little stone dimension is finite. And even more precisely, we can bound the regret achieved by a learning algorithm by square root t times the little stone dimension. So we sort of have a complete picture of what is learnable in this model. However, one perhaps limitation, or I guess it's a very difficult model in the sense that almost all interesting function classes that we care about have infinite little stone dimension, i.e. they are not online learnable. So this applies even for the simple class of thresholds on the unit interval. And this is witnessed, for example, by having an infinite little stone tree starting from 1/2 and then branching, where each basically path in this tree can be realized by a threshold on the interval. And so any learning algorithm can be forced to make infinitely many mistakes. So given this perhaps a bit pessimistic situation, we can't even online learn thresholds, as a learning theory community, we developed several techniques to bypass this lower bound. So I'll just mention a few examples. One famous structural assumption is that of the margin, which is specific for linear predictors, so where we assume basically that there's a ground truth linear separator that separates the data with some margin parameter gamma. And under this assumption, we know of some mistake bounds that can be achieved, one via the perceptron algorithm, and another perhaps less known bound is using cutting planes method, where we achieve d log 1 over gamma. So we have sort of two styles of bounds, and both are useful depending on the regime. Now, a more generic approach, and perhaps more recently, people developed the smoothed online learning framework, and we have had a tutorial about this on Monday, so I'll not go into the details, but suffice it to say basically that we restrict the adversary to draw an instance from some sigma smooth distribution. Sigma is the smoothness parameter. And under this like framework, it can be shown that we achieve regret of square root t times VC dimension times log 1 over sigma. So the idea here is that based on like introducing some extra assumptions or some structure, we can bypass the dependence on the Littlestone dimension. So in our work, with a similar aim of bypassing this dependence on Littlestone dimension, we like to take a different perspective where we would like to relax the benchmark that we compete with. So instead of competing with the best in the class, denoted by opt, we will explore basically competing with relaxations of opt, parameterized by some parameter gamma, and think of gamma as this like generalized margin parameter. And this idea has already been proven very useful in other contexts. For example, in Best Paper Award in COLT last year, it has been shown that there's provable computational benefits of this perspective in agnostic pack learning. In the context of online learning, like most examples that we know of are limited to the hinge loss and in particular to linear classifiers. So we can compete like with the smallest hinge loss achieved by a linear classifier with a regret bound of square root t over gamma squared. So the idea of our work is we aim for new generic regret bounds, and by generic meaning we want them to apply for arbitrary function classes, not just linear predictors. And we aim to replace like Littlestone dimension with more favorable complexity measures such as VC dimension. And at the same time, we want to pay as little as possible in terms of dependence on this, like the margin parameter. So we would like to get this log 1 over gamma factor as opposed to like gamma or like polygamma dependence. Okay, so now I'll survey the results that we have in this work. So the first result is, first we study this relaxation of opt, which we denote here by opt gamma perturbation. And it looks for the best classifier in the class that can basically robustly label the online sequence, the XTs. So if you think of linear predictors, this translates to finding a linear separator where it doesn't really intersect like balls of radius gamma around the XTs. And one way to understand or like to gain intuition about this is to think about when does it equal 0. So this benchmark or this opt will equal 0 if and only if there's a classifier in my function class that can label the entire ball around each online point xt with the label yt. Okay, so this can be thought of as a generalized version of the margin condition in half spaces, but we can define it for an arbitrary function class as long as we have this metric structure. So what results do we show for this competing with opt? So for the upper bound, we show that we can basically, for any metric space, we can compete with opt gamma perturbation with a regret bound of at most square root t VC dimension times the log covering number at scale gamma. Now let's instantiate this bound in, say, like the unit ball in RD. So we get this kind of bound where we get a square root t VC dimension times log 1 over gamma. So we sort of, okay, we achieve this goal of bypassing Littlestone dimension, and we pay this log 1 over gamma factor with an additional dependence on this dimension. There's this additional factor d, but we show in general that this is tight in the sense that for any metric space, there exists a class where the bound is tight. So we can't really sort of improve the upper bound further in general. We can improve it in some cases, which I will get to at the end of the talk. Okay, so this is the first relaxation. Another relaxation that we explore is sort of doing a Gaussian smoothing operation on the function class. So this is another opt that we study. We denote it here by opt Gauss, sigma, and epsilon. So sigma is going to be the scale of the noise, or you can think of the smoothness parameter. And denoted here by yellow, so this is sort of the smoothed function, where we take a binary function, and then we add noise to it, and we get this smoothed function. And now we want to compete basically with the best smooth function in the class after doing this smoothing operation. And we have sort of this margin loss here with this parameter epsilon. Now, with this relaxation of opt, we similarly show like a similar result where we can compete with the best, or we compete with this opt, the smoothed opt, and achieve a regret bound of square root t VC dimension, log the covering number in L2. So we get a like quantitatively similar bounds for competing with this opt. And similarly, if we instantiate this in RD, we get this t VC dimension d log 1 over epsilon times sigma. And yeah, we show that for x being the unit interval, this bound is tight. Okay, so one final relaxation. And this actually, so classically in the literature, this has also been studied, and this is sort of a generalization of the margin condition for real valued function classes. So here, f is going to be a real valued function class between -1 and 1. And in this setting, so prior to our work, we have known like some regret bounds. So it can be shown that we can achieve regret bound that is at most sequential Rademacher complexity divided by gamma. So we have this poly dependence on gamma and also dependence on the sequential Rademacher complexity. Now, what we show is that with an additional assumption on the function class, mainly if the function class is Lipschitz, then it is possible to improve the regret bound to something that depends on the pseudo dimension of the function class or the fat shattering dimension. So these are more like batch complexity measures, and times the log the covering number, where basically the Lipschitz constant appears in the scale of the cover. And yeah, some lower bounds. And finally, to wrap up, so specifically if you study the class of half spaces, so one thing we show is that all of these relaxations that we propose are equivalent. So quantitatively, they're actually equal to each other. So, and we can improve the regret bound for half spaces by removing like a d factor. So instead of d squared, we improve to d, and this is by exploiting the parametric structure of half spaces. That is all, and I'm happy to take questions.
Hi, so a lot of these improvements, they're all kind of geometric or based, right?
Yes, to some extent, yes.
What do you hope for similar things in non-geometric hypothesis classes?
It's a good question. So yeah, a lot of the results that we use, for example, have the assumption that the metric space is, or like the instance space has a metric structure. Yeah, and it's a good question whether it's possible to sort of take this perspective and extend it further to maybe metric, like instance spaces without a metric structure. Yeah, it's a good question. I think it depends on the relaxation that you, like that one would study. Yeah.
Okay, thank you.
Yeah, thank you.
So when you go from the average case notion, sorry, the worst case notion to the average case notion in terms of perturbations, is there an extra root d factor or something that comes up?
So if you talk about, if you mean the first result, for example, this one.
Yeah.
Yeah, so this is sort of the regret band that we get. So VC dimension times log covering number, and we have this extra dependence on dimension. Like if we, yeah, and this is like unavoidable in general. Like we have a lower bound.
Oh no, I mean when you think of the Gaussian perturbation. So
Okay.
is it the same as the radius that comes up for the Gaussian?
It's the same, yes. To
Or is there an extra factor?
so here there is this log 1 over epsilon sigma. So these are, so epsilon and sigma are the parameterization, the parameters for the relaxation, and there's this extra dimension. So it's this roughly the same bound.
So I guess I was confused by this too. So the second to last slide you gave.
Yes.
So really they're equivalent for
For-
particular for all values of gamma. It's not that for each gamma there exists a gamma prime. And
So for half spaces specifically.
okay.
For half spaces,
okay.
these relaxations are equivalent, and this is actually for a specific choice of gamma. So we have to choose gamma, sigma, epsilon, such that gamma is equal to sigma times the inverse CDF of.
But such an equivalence probably doesn't hold beyond that half.
Exactly. Yes. 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 So the point is that this will give you like sort of different relaxations, and you would apply, or it depends on the structure or the knowledge you have about the data, so that one relaxation may be more useful than another.
Maybe just in the interest of time, we can take
Yes.
any further questions offline. And if we could have the next speaker come on up. Maybe we'll actually kind of move forward and come back to this talk. So let's have the speaker after this come up. And again, there is some space in to sit. If people are standing and they want to sit, they can fill in. All right, we'll just skip him and put him at the end. Okay, great. Now let's hear about sample-efficient downstream swap regret and omniprotection.
Hi, thanks. I'm Myra. I'm going to be talking a bit about omniprediction and swap regret for nonlinear losses. This is joint work with Julia, who couldn't be here today because of visa issues, and also Aaron, my advisor. So just to set things up a bit, predictions inform our actions in a lot of different contexts. Just as a concrete example, imagine you want to help people invest their money. So you're going to make predictions about how well a certain stock is going to do, for instance. Someone's going to look at your predictions and decide whether to buy. Okay. Maybe the price actually drops, and then they will lose some amount of money. So what I've described here fits into this framework where a forecaster makes some prediction, an agent takes an action based on the prediction, and then suffers some loss based on their action and then the outcome. So what should the forecaster do? Well, it's probably unreasonable to ask them to predict the entire distribution, but luckily we often don't have to, right? So for L2 loss, squared loss, we predict the average. For L1 loss, on the other hand, we want to predict the median. So already here we see that prediction targets vary with the losses we care about. So a prediction that's useful for one agent, say with L2 loss, may not be useful to another agent, say with L1 loss. And in the example that I just gave, you can think of scenarios where different investors have different risk tolerances, and maybe so their losses are different in that sense. Okay, so the question we're asking here is, can we make predictions that can be useful to a lot of different agents, potentially with different losses? So what do I mean by useful predictions? We're going to say predictions are useful if they can be post-processed in some way to obtain good actions for all the agents. Okay, and I want to expand on two things here. So first of all, what do I mean by this post-processing? So just taking us back to the formal setup, imagine you have a family of loss functions. So this is going to be the family of losses that we're going to want to give good guarantees for. And we're going to talk about an online setting. So every day, the forecaster will make some prediction. Any agent with a loss in this loss function will look at the prediction and then take some action as a function of the prediction. So for the rest of this, I just want you to think of this post-processing step as the optimal post-processing. So the agent will take the action that minimizes their loss given the prediction. So in other words, they best respond to the prediction according to their loss. And then they'll realize some loss. Okay, everything I've described here is in the online setting, but with these standard online to batch conversions, we can get results in the batch setting as well. So later on, I'll reference results in the batch setting and just know that these are just via standard reductions. Okay, so now that we know what this post-processing step is, what do I mean here by good actions? So one answer I could give is, actions are good if we couldn't do better, even if we had used another policy. So a policy could look something like, buy if there has been an upward trend, sell if there has been a downward trend, or it could be a regression model that you already have. Okay, and this This is exactly like formalized through this notion called omniprediction, first introduced a couple years ago in 2021. So omniprediction asks that for all the losses I care about, my loss is not too different from the loss of the best policy in the class. Okay, so I have this class of policies, and I want to make sure that I'm making predictions such that when agents take actions based on the predictions, they won't suffer a loss that's too much different from the best policy. Okay, I could give you another answer to this question, which is that like actions are good if we couldn't do better in hindsight had we like been able to swap out each action with another action. Okay, so for instance, this looks something like on the days I bought like Apple stock, I could have bought Nvidia stock. And this is like formalized through this notion called swap regrets. So like predictions have no swap regret if the realized losses on the sequence of actions is not too different from like the loss had I applied this like swap function to my sequence of actions. So the literature has like primarily given us these two answers to this question, like how do we make predictions so that agents with like potentially many different losses can choose good actions. And so what we do in our work, we kind of offer a unifying perspective on both like omniprediction and swap regret. So our answer to this question is actions are good if we couldn't do better, even if we could modify each action using a different policy in hindsight. So for instance, this could look like on the days I bought Apple stock, like I could have decided to use a model trained on like market trends. And we're gonna call this decision swap regrets. And I don't want to dwell on the definition too much, just to say that it generalizes both omniprediction and swap regret. So it kind of offers this nice unifying framework to think about like predictions that give good guarantees for many different agents. And in giving this unifying framework, we're able to obtain results for decision swap regret that translate to stronger results for both omniprediction and for swap regrets. So just to highlight what we show. So up to this point, we only knew how to get swap regret for families of linear losses. And we show how to do this for families of nonlinear losses. The omniprediction literature has considered families of nonlinear losses, and this is work done by Abhishek and Princewell. And they show that you can do this in the batch setting with sample complexity that's exponential in the error parameter. And we show how to reduce this to a polynomial sample complexity for broad classes of nonlinear losses. Okay, I want to, for the rest of this talk, I'm going to like give you a peek behind the techniques because I think the techniques are also, they also very nicely tie together both literatures in some sense. So for now, let's just assume that the losses we care about are actually linear. Later, I'm gonna tell you how to like extend this to nonlinear losses. So for omniprediction, if predictions are calibrated and satisfy this condition called multi-accuracy, that gives you omniprediction. For swap regret, we know that if decisions satisfy this like weaker notion of calibration called decision calibration, it gives you no swap regrets. So we show that if predictions satisfy decision calibration and they satisfy this thing called decision cross calibration, then you get no decision swap regrets. So again, decision calibration kind of guarantees the no swap regret part of it. And if you add on this condition that we call decision cross calibration, if you're familiar with like notions of multi-accuracy, you can kind of just think of it as an alternative for multi-accuracy for like a decision setting. Then you get this guarantee that also allows you to compare to like alternative policies in hindsight. So the main workhorse behind this is this notion of decision calibration. And this is the weaker version of calibration that exactly lets us get the exponential improvements in sample complexity. So in the interest of time, I'm not going to go through what they are, but feel free to ask me after. So I promised you results about nonlinear losses, and the one-word answer to this is just approximation. So imagine you have a nonlinear loss, and I could give you a linear loss that closely approximates it in a higher dimensional space. So this linear loss lives in a higher dimensional space defined by some basis transformation. And if I can do this, instead of predicting the actual label, I'm going to predict the basis transform label, which might live in this higher dimensional space. So now we're just gonna be working with like essentially linear losses, and we can kind of go back to the techniques we knew before. And so we're able to construct these basis transformations for some pretty broad classes of losses, and the size of the basis is essentially going to be the dimension of our prediction space now. So putting it all together, for certain classes of nonlinear losses, we can find these like linear approximations. And now that we're kind of back in the linear world, we can apply, so like if we know that if our predictions satisfy decision calibration and decision cross calibration, then we'll get no decision swapograph for nonlinear losses. And just to like wrap things up in a theorem, for the family of one-dimensional Lipschitz losses, we get rates that depend polynomially on both the action space and are sublinear in the time horizon. And for the batch setting, this will translate to like sample complexity that's polynomial in epsilon. Thanks.
Does anyone have any questions?
A quick question. How does this relate to the swap omni-prediction business that Parikshit and Kim had?
Yeah, I think swap omni prediction also lets you, so in our notion of decision swap regret, your choice of policy could depend on the action. I think in swap omni prediction, the choice of policy could depend on the prediction. So in that sense, it kind of requires calibration because you need to be able to give guarantees for the predictions themselves.
Your notion does not imply multi-accuracy, multi-calculation. They show the swap omni-prediction strategy. They have this whole tree of things. We can take it offline.
Sure, let's take it offline.
Just another question. So, what notion of approximation do you need? Like, when you're approximating this nonlinear function by linear thing in the lifted space, it's not like a kernel, right? So, what notion do you need?
Yeah, so we just require their outputs to be close, point-wise. Yeah.
Maybe we can take the rest of the questions offline just in the interest of time. Let's thank the speaker again. And we're going to go back one speaker. So, yes, wonderful.
If you could please reduce the spaces to let some standing people in, just if possible. Thank you.
Should I use this? Or?
Yeah, it might be helpful.
Okay.
Maybe just wait as people settle down.
Yeah. Hi.
Yeah, I'm just
Huh?
Okay, great.
Said hi.
Let's now hear Eric talk about truthfulness of decision theoretic calibration measures.
Yeah, thanks for having me. Okay, so I think in the earlier talks, you've probably seen a lot of different definitions like swap regret, decision calibration, so on. A lot of calibration measures. So today we're going to take a higher level look and sort of ask, okay, if we're sort of going back to fundamentals and asking how are we supposed to define calibration, what is sort of the right way to think about it? And today we're going to be looking at a very specific question, which is how truthfulness and decision theoretic guarantees interact. If that doesn't make sense, hopefully it will by the end of the talk. And this is joint work with Mingda, who unfortunately couldn't be here. But yeah. All right, so we're going to work in the online probability forecasting setting. Sorry, let me get my clock going. And this is a setting where you have multiple time steps, and sort of before each day you declare what is the probability, let's say that it rains, 75%, and then nature says, oh, it does rain, and you sort of just repeat this over multiple iterations. Calibration, I'm not sure if it's been defined yet, is just saying that if I look on the level sets of my predictions, I am basically unbiased. So for example, if I look at only the days where I forecasted a 75% chance of rain, then of those days, about 75% of the time it should have rained, right? It's a pretty reasonable like frequentist notion of what Bayesian rationality should look like. And the way you would write it formally is just, I look at the time steps where I predicted a level set alpha, and it did rain, divided by the total number of level sets where I did predict alpha in the first place. So I'll just let you stare at that for a second. This is just the classical way that we define perfect calibration. And generally, there's like pretty good agreement that like, okay, this is what perfect calibration is. And calibration is really nice. Well, there's several reasons people care about calibration, but one of the bigger, more modern reasons is that it basically gives you nice like downstream decision theoretic guarantees. So what do I mean by that? If your weather forecaster is calibrated, then what that basically tells you is that you can rely on them to make decisions, right? So if you just sort of treat their forecasts as the true probability of rain, you really won't lose out that much as measured by like the normal things like swap regret and so on. And this is like a very classical theorem, like just to be a little more formal. If I have a utility function, that maps from a set of actions to, and like whether or not it rains to a utility, and sort of I define an action as this like a y hat, where y hat is a forecast, as being the best action to take, assuming the forecast is true, then I can define this notion of swap regret with respect to a forecast, right? It's saying that if I have a set of forecasts, y hat, and I sort of like act as if that forecast is true, what is the swap regret I will incur? And a very classical theorem tells us that, if the predictions are calibrated, then pretty much no matter what your utility function is, you won't have swap regret, like external or internal regret. This is like very powerful. As you see above, like it's nice because it means that like if you have players in a game and they're all working on calibrated forecasts of each other, they'll quickly converge to an equilibrium. And it also gives rise to things you've seen like earlier today, like omni-prediction. So, if we're So I guess this makes sense for like perfect calibration, but then the question is, okay, what happens if we don't have perfect calibration, right? Like how do I measure how close to calibrated a set of predictions is? This is where we start to talk about calibration measures. So calibration measures are simple. They just take in a set of events, like whether it rained or not. We'll call those x1 through xt. And they take in a set of predictions, so p1 through pt. These are real valued, what do I think the probability of rain is? And it gives us sort of a score. It tells us how close we are to being calibrated. And like I said, there's a lot of different calibration measures, but if we sort of ask ourselves, what should a reasonable definition of calibration satisfy? There's a few things we can say, right? The first is like pretty characteristic of calibration, which is that if I have a set of good predictions, I guess I won't formalize that, but like if there is a 50% chance of rain every day and I predict exactly 50%, then my calibration error should be low, right? So this is not something that a proper scoring rule like Breyer's score can satisfy, where you would inevitably pay variance. Sort of like along with that comes the decision theoretic guarantees, right? Good predictions should have low calibration error, and it should go the other way around too, in that if my calibration error is low, then I should be able to rely on it. So hopefully those are two properties that I don't have to defend too hard. Sort of the next thing that seems reasonable for a definition of calibration is that if I have a set of bad predictions, let's say it'll rain with 50% chance every day and I predict a 70% chance of rain every day, my error should be high because I'm pretty like consistently biased. And along the same line, in the reverse direction, if I know what the probabilities will be and I intentionally pick a different probability, something that's off by a lot, I should, that should cause my calibration measure to become worse. My calibration measure should not incentivize me to predict incorrectly. And sort of the last thing, maybe this one isn't as important, is just saying that has to be attainable, right? We don't want a notion of calibration that is just like impossible to get. Great, so these are all like pretty good goals to aim for. So let's take a look at all of the calibration measures and see which of these they fulfill. There's a lot, so I'm leaving out like 99% of them or something. Oh, sorry, before I do that, let me first define some things formally. So decision theoretic we saw before is just saying that if my forecasts are epsilon close to calibration, according to how I'm defining calibration, then any agent should have a swap regret of at most epsilon if they if they use my forecasts. And truthfulness, I'll just formally define as well because it's also a little unintuitive, is just saying that, okay, let's say that the probability of events is being sampled from some distribution. This can be like a joint distribution. It doesn't have to be a product distribution. Now, the one thing I can do is I can just predict what the true conditional probability of rain will be, right? This is sort of the best thing that I can do. This is also saying that like I'm predicting consistent with my beliefs. But I can also ask, what is sort of the optimal prediction? And if I have a much larger incentive to predict the optimal prediction versus the truthful one under my calibration measure, that's probably a sign that my calibration measure is, maybe not that great of a measure. Like, even if you know what tomorrow is going to be, you're sort of incentivized to lie, right? So those are the decision theoretic and truthfulness calibration measures. Those are the two I just want to highlight because, if we look at, all of the calibration measures, like I said, this is a very small subset. None of them actually satisfy all of these guarantees, right? So expected calibration error, this is like the good old if you know textbook calibration error, that's what ECE is. There's also like smooth forms that are more efficiently attainable, lack decision theoretic guarantees, Kleinberg's U calibration, proper scoring rules. We had a recent paper where we talked about like truthfulness as well, but that wasn't decision theoretic, and that's not very encouraging. And just as a quick exercise, we can take a look at why U calibration fails truthfulness, right? So U calibration is a very nice notion of calibration. It gives you decision theoretic guarantees. You can get it at like pretty fast rates. It's complete, it's sound, has all the nice properties you expect from calibration. But here's like a pretty clean example of why it's not truthful. So say that the true probability of rain sort of alternates between 20% and 80% each day. And you can just give those forecasts, but what you can also do is you can just exaggerate your uncertainty, right? You can say, oh, there's a 40 or 60% chance of rain. And that is actually something that benefits the reliability of your predictions. So if you look at the external, or if you look at the swap regret of your downstream agents, they'll actually be better off if you sort of like exaggerate your uncertainty. I do want to point out this is a bit different from online learning. So like online learning, we know that like stability helps when you're sort of like reporting on the past. This is like more about the future. Yeah, so this is an example of why calibration measurement might not be truthful, right? Like you can sort of like reward hack it. It's like Goodhart's law. Okay, so the unfortunate part is this is sort of an unfixable problem in that, all of the good things that we want to talk about with the calibration measure, we basically can't get simultaneously. If you're a AGI pilled person, you can say the alignment problem is unsolvable for forecasting. Okay, so why is this the case? We can actually come up with a situation where in order to be a reliable predictor, in order to give your downstream agents sort of like make sure that their regret is not like, linearly growing, you have to lie quite a bit. And this is the construction. I'll just like hand wave it. You first predict that there's a 50% chance of rain, right? Let's say you're trying to play the adversary, and you look at whether it does rain or not. You have some external dice. And let's say it does rain. Then you're sort of doing this like binary search problem where you're trying to find a threshold. And so if it rains, then you move up to 3/4. If it is sunny, you move down to 5/8. And what happens is that the true probabilities are basically always going to lag around that like optimal threshold. And so what you'll have is if someone is just trying to follow these true probabilities, like they're trying to actually forecast the future as it is, they'll end up paying like linear in any reasonable calibration measure. But if you had just predicted 1/2 through the entire process, you actually would have been fine. your calibration measure, for any reasonable calibration measure, can be close to square root. But this actually is not a serious impossibility. With these impossibility results, we kind of have to ask ourselves, is this a real thing, or are we just like doing math in theory land? This is a case of doing math in theory land, because you actually can, if we move to a smooth setting, this impossibility no longer remains. So what do I mean by smooth? For this sort of counterexample, this pathological example, I needed very precise control of what the true probabilities are. If I instead imagine that these true probabilities are sampled from a prior, it can be an adversarial prior. I'm just saying that we're not going to allow ourselves to focus on measure zero cases. Then there is a notion of calibration that satisfies all 5 of the desiderata that we would hope for. And it looks pretty similar to expected calibration error. It's just instead of conditioning on a level set, we condition on a sub-level set. In the interest of time, I won't talk too much about it, but there's one technical nuance where you kind of have to randomize the time steps that you take over it, just uniformly. But yeah, so that's step calibration error. And then, if you fill it out, then we now have this thing where you can't satisfy everything, but you can have a notion of truthfulness in realistic settings. And yeah, that's it. There's a QR code for the paper, and thank you for having me.
Maybe in the interest of time, we can just have one really quick question, if anyone has that.
I guess I just had a kind of basic question. What does it mean to make a truthful prediction in this online setting where there's no reason you need to assume that nature makes samples outcomes from any kind of reasonable probabilities, right? Outcomes are chosen adversarially.
Yeah.
How would you know that the learner, say, knows these probabilities if there's no probabilities to talk about?
Yeah, so truthfulness doesn't always make sense. So all we ask is that if truthfulness does make sense, if nature is sampling from the events from a joint distribution, then then predicting the probabilities of the conditional distributions is pretty reasonable. So we're just asking in the settings where truthfulness is a concept that makes sense, that truthfulness is satisfied.
Yeah. Okay, great. Let's thank the speaker again and maybe take all questions off. Okay, great. Let's learn about computing optimal regularizers for online linear optimization.
All right, yeah, thanks. I'm going to talk a little bit about computing optimal regularizers for online linear optimization. This is joint work with Kashar, who unfortunately couldn't be here due to visa issues, and Stephanie, both at MIT. So, many of you are probably familiar with online linear optimization, but let me remind everyone and formalize notation. So, this is perhaps the most fundamental version of external regret minimization. It's a game between a learner and adversary over T rounds. In every round, the learner will choose some action from, and this is important, I'm going to say they're going to choose some action from some convex subset of Euclidean space. At the same time, or obliviously or whatever, an adversary is going to choose a linear loss function, also from some convex set L. And the learner is going to incur a loss which is just the inner product of their action and the adversary's loss. And what the learner wants to do, of course, is they want to minimize their total cumulative loss. How we actually formalize this is we formalize this by the objective of minimizing regret. And basically, the learner wants to minimize the difference between their total loss and the loss of the best fixed action in hindsight. Right? So this problem has been studied a lot in the online theory community, online learning community. We know many algorithms that get sublinear regret, and we know that, in general, you should be able to get square root of T regret for basically any collection, any set of action and loss spaces. All right. I really want to say, there's many reasons why online linear optimization might show up. One specific motivation for this work is a lot of problems like the calibration talks we just saw, and also learning problems that stem from swap regret minimization or Blackwell approachability lead to online linear optimization problems with, maybe I'll call them strange action sets and loss sets. So instead of, you're picking actions from the simplex and losses from the L infinity ball, or actions from the L2 ball and losses from the L2 ball, you might end up with weird cases where you're picking, actions from some weird polytope, like the polytope of all doubly stochastic matrices. And so part of this talk is, what do you do in those cases? Okay, so we know how to solve those cases too. There's a very powerful class of algorithms for this problem, the class of follow the regularized leader algorithms. These are basically algorithms that approximately play the best action in hindsight, right? So at every round t, what the learner will do is they're going to choose the action x sub t. That'll minimize their historical loss plus some regularization term for some convex regularizer f. And you can show that, yeah, if f is strongly convex, then FTRL is going to obtain some square root of t dependence. And this talk is really about what's this constant factor in this square root of t dependence. And the constant factor is going to depend critically on both the choice of the regularizer f and also these two sets x and L. One sort of canonical example here is if you're just in the standard learning with expert setting, right? So this is the setting where your action set's the simplex. You're basically choosing distributions over d different actions. And your loss set is the corresponding L infinity ball. So they just have bounded losses. We know that if you substitute the quadratic regularizer, just f of x equals x squared, you'll end up with square root of dimension times t regret. On the other hand, if you do something smarter, if you use the negative entropy regularizer, which corresponds to running multiplicative weights, you know that you'll end up with square root of t times log dimension regret. So it's like an exponential improvement in regret. So the question we're trying to basically study in this paper is, if I just give you an action set x and a loss set L, what is the optimal regularizer to minimize this, that achieves this optimal rate, this optimal constant in front of the square root of t? All right. So it's a pretty fundamental question, I'd say, in like online learning. I think fairly little is known for sets outside of like the standard sets I mentioned. So we know that square log d is tight for the simplex. We know that constant is tight for the L2 ball. People know results in other cases. But if I just come to you with, here's a weird action set, here's a weird loss set, it's not so clear what regularizer you should pick. And so in this paper, we make some progress towards answering this problem. So first, we show that there's many other algorithms you can imagine running aside from FTRL. We show that, first of all, there is some version of FTRL which will give you a near optimal regularizer. And by near optimal, I mean within some universal constant factor of the optimal rate. Secondly, we will give an algorithm to compute such a regularizer. Spoiler, it won't be very efficient, but it's the first algorithm, at least I know of, that will achieve close to optimal rates for this problem. And one technical note to point out, these results only apply to centrally symmetric sets x and L. For a bunch of technical reasons, it's important that these sets define valid norms. But I would guess that it probably is extendable to beyond this. Okay, so briefly, this first contribution, the existence of a near optimal regularizer. So really, most of the work was done for us already. There's this great paper by Srebro et al. Called The Universality of Mirror Descent, where they basically show that mirror descent, which basically you should think of as FTRL, is within log t times universal constant of the optimal rate for any online convex optimization problem. It turns out if you look at the analysis closely, you can see that in the case of online linear optimization, you don't pay this extra log t term. And so as a byproduct of this, you can show that there is some instantiation of FTRL which will get you within a constant factor of the optimal rate. Okay, so you might ask, does this just also give you an algorithm? The catch is that these techniques are very much not obviously computable. They basically phrase the optimal regularizer in terms of these optimal martingale type sequences. You have to basically solve a supreme problem where you try to optimize some objective over all martingale sequences in your action space, and it's not very obvious how to do this or how to even prove that you've gotten within epsilon accuracy of optimal here. So instead we take a slightly different approach. Okay, well, I guess let me tell you what we do, what the algorithm sort of looks like. So we give you an algorithm that'll take oracle access, like separation oracle access, membership oracle access, whatever you like, to the action set and loss set as input. It'll run in exponential time. I'll say more about this later. And it'll output a regularizer f that you can then query efficiently, although it still takes a lot of space to store, that guarantees a constant factor within the optimal regret bound. And one thing to know is that this runtime is independent of the time horizon, and yeah, it's a constructible, computable solution to this problem. Okay, so how do you find the optimal regularizer? So there's basically 3 steps at a very high level. The first is, and this is sort of like a old observation that we make a little bit more concrete, finding the optimal regularizer corresponds to finding a convex function that's as strongly convex as possible with respect to a specific norm, while still being bounded on a set. Then we tried to phrase this as like an optimization problem that you can solve. So optimizing over the set of all convex functions is hard. We tried to optimize over a finite parameterization of convex functions. To do this, we introduced a new technique called quasi-quadratic approximation, which I'll mention in a second. And then finally, once you have this, you can sort of just optimize over the set of quasi-quadratic approximate functions in polynomial, well, not polynomial time, but in finite time. All right, so like I was saying, it's known that okay, so a function f is alpha strongly convex. It's just sort of like a generalization of the standard Euclidean strong convexity if it satisfies that expression up on the slides. And it's sort of known from the standard analysis of FTRL that if you have a function f and it's unit bounded over your domain, and it's also alpha strongly convex with respect to the dual norm induced by the loss set, then you can get rates that are square root of 1 over alpha. It's not too hard to show that this is basically tight by following this earlier analysis of Sri-Brodel. So in particular, if you have the optimal regularizer, like it's going to be, there's going to be some alpha strongly convex function that meets this, that could do that rate. Okay, so this gives you an optimization problem of how do you find the most strongly convex function over some domain. One intuition here is that you want to control the second derivative. So like, one thing you can do if you want just, if I gave you a function and I said it should have first derivatives at all these points, you could just take the maximum of a bunch of linear approximations, take the maximum of a bunch of linear functions. You can try doing the exact same thing with quadratic functions. Just take the maximum of a bunch of quadratic functions to control the second derivative of your convex function everywhere. Unfortunately, an approximation centered at some point x not in your domain can be overshadowed by another one that's centered very far away. So you need some sort of local dominance. And very briefly, because I'm running out of time, what you do is you just add this decay term. So you add a little cubic decay term, and this lets you produce this class of regularizers such that it's strongly convex. You can specify how strongly convex it is at each point without affecting the strong convexity at other points of the grid. All right. I'm out of time, so I won't say too much. We do have a lower bound. You might say, like, okay, this algorithm kind of sucks because it takes exponential time. There's a lower bound which shows that basically computing the rate given a set x and l is computationally hard. But I do want to say that I do think that, in some sense, this algorithm does suck. And I really do want to find a better polynomial time algorithm that, given, just separation oracle access to x and l, will get you something maybe within the log d factor, but some constant factor of optimal. And thanks.
So again, maybe in the interest of time, we can have just one quick question and maybe take the other questions offline.
Hi, thanks for a nice talk. So in prior work where they have this extra log factor, they also show that if you can achieve a regret bound that is like t to some other power, that you can also do with mirror descent universally. Do your results extend to that case?
Yeah, so we haven't thought about the case of like a convex optimization where you can get bounds better than square root of t. It's possible some of these results extend, but we haven't thought about it.
Okay, thank you.
Let's thank the speaker again. Great. Now let's listen to Zach.
Thanks everyone for coming. So this paper is about the standard constrained online convex optimization setting. So in this setting, you have an agent or an algorithm that interacts with an environment. It outputs some iterates WT in some constraint set K. So this could be a subset of the Euclidean space. And then the environment reveals a convex loss function. And the goal in this constraint OCO is to ensure a small regret. So typically, if you have T rounds, you want to have a regret that's sublinear in T. And just quickly for motivation here, why we care about OCO. Well, OCO generalizes offline and stochastic optimization via standard online to batch conversion techniques. But also more recently, it has been shown to generalize also non-convex optimization. So you can go from non-convex to just OCO. I think this is very nice. And so for this reason, it's very important to design OCO algorithms that are as efficient as possible. And in particular, we want algorithms that have low per iteration costs without sacrificing too much the optimal regret. So let's quickly look at what algorithms can achieve and what's their cost. So if you look at just standard online gradient descent, it achieves the optimal root T regret, but then as soon as the iterates step outside of the feasible set, you need to do Euclidean projection. So you pay for this C proj. There are projection-free algorithms like Frank-Wolf, and in this case, you swap out the potentially expensive projection by a linear optimization. That's where this cost comes from. But unfortunately, you do sacrifice the regret. So now you achieve this T to the 3/4. And this bound, I think, has been known for more than a decade. It hasn't been approved on, and there's no lower bounds. So that this could be an interesting problem to tackle. And then more recently, we had this paper that achieves a root T regret. I'm going to explain what kappa is in the next slide. But we achieved this using a different type of oracle. Instead of linear optimization, we use a separation oracle. And in general, these oracles are not necessarily comparable, but for many practical settings, a separation is still very cheap compared to a projection. And I would say that this is kind of the first algorithm that achieves a root T regret in the projection-free setting. And it has been useful even outside the OCO setting, where it inspired some quasi-Newton methods to achieve global superlinear rates. And he also inspired some design of an extension function in the convex bandit setting. All right, so what is this kappa? Well, kappa is in a way a measure of the conditioning of the set. So if you have your set K and you look at the largest ball that is contained within the set, let's say this has a radius little r, and then you look at the smallest board that contains the set, and that's big R, then kappa is just this ratio. And in general, for many problems of interest, kappa is not too large. So this table was coming from the Colt paper in 22. As you can see, for most settings, kappa, I mean, it's dimension dependent, but it's not too large. The problem is, in general, you can always have bad settings where the set is very ill-conditioned, in which case kappa can be arbitrarily large. And so because kappa multiplies the regret, this is not desirable. So a solution attempt to this is you can maybe pre-process your set to make sure that kappa is bounded by some polynomial of D. So you can actually always do this by transforming the set into isotropic position, right? There's two issues with this. First one is this, like the best algorithm we know of for doing this costs D to the 4 calls to the separation oracle, so that's not ideal. And the second issue is it actually does not necessarily help you get rid of this kappa, because once you reparameterize, you may inflate the norm of the gradients. So if the old regret was like this, where you have G kappa square root T, where G is the maximum norm of the gradients, once you reparameterize, you may, the parameterization matrix may reintroduce this kappa term. So this does not really solve the problem. So the main result of this work is we found another approach. Instead of reparameterizing the set, we have another approach that essentially pushes this kappa term into a lower order term that does not depend on the number of rounds. So now the main regret term is square root dt that is independent of kappa. And in terms of the computational cost, it's not much worse than the previous algorithm. We still have the same number of calls to the separation oracle. We do have an additional d square, which is slightly worse than the previous method. So the key techniques here is, by the way, I should quickly say that the previous approach in call 22 was based on the reduction from OCU over the constraint set to OCU over a ball that contains the set. So now what's different with the new technique is that instead of, we reduce OCU over the set K to online X-concave optimization over a ball that contains the set, right? And the reason this is helpful is that there exists algorithm for this online X-concave setting that are almost preconditioning free. So what this means is they act as if you've already applied the best reparameterization to the set. So that's the advantage of doing the reduction to online X-concave optimization. So when we go to online X-concave optimization, the algorithm that we apply is online Newton step with a log barrier over the ball. And the reason we do log barrier over the ball because it enables a much more efficient algorithm than just a standard ONS. So standard ONS, you still need to do projections or this generalized projections over a ball. And these require SVD or like an inverse of a matrix, so they can be up to d cube. But what's very nice when you add the log barrier for the ball, you can do an amortized technique to only pay d squared per round on average. And so just quickly how the reduction work is you have a wrapper algorithm A, so this is the main algorithm. It wraps around a base online X-concave optimization algorithm. So this X-concave optimization algorithm always outputs iterates in the ball. And because it has a log barrier, when you do ONS, the iterates are always guaranteed to be within the set. And then in the workings of this wrapper, you take the iterates of algorithm B and you somehow map them to the set K. And you can do this with only a small number of calls to the separation oracle. Okay? And the specific design of this approach ensures that the regret of the wrapper algorithm is going to be less than eta r squared t plus the regret of algorithm B. And here the regret of algorithm B is going to be with respect to some X-concave losses. And so we know that for X-concave losses, you can achieve a logarithmic regret. And so we get a total regret of this form. And so now you can see that if you tune eta properly, you will get your square root dt, and then you have a lower order term coming from, there's some bound on eta that we have to specify, and that gets you the lower bound. Okay, so obvious limitation is that even though we pushed this kappa into a lower order term, this can still be arbitrarily large technically. So we would like to avoid this. And ideally, we want some fully preconditioning free approaches. And actually, this is coming up soon on archive, where like we completely remove kappa from, well, it's inside logarithmic terms now. But there still remain questions about lower bounds in general, for not just separation-based algorithm, but also for linear optimization-based algorithms. And yeah, I can take some questions.
We actually have a few minutes for questions. Does anyone have any questions? I maybe have one. So first of all, can you talk a little bit about the intuition for why this kappa has to be centered at the origin and why it kind of is naturally appearing in the algorithms that you're talking about?
Why does kappa
or
have to be
does the
centered?
kappa, like the kappa, this asphericity, do the spheres have to be centered at the origin? Because in the pictures they were all, and could you maybe go into some intuition as to why this?
Yeah, well, so if the origin is close to a boundary of the set, then that's a setting where it's very ill-conditioned because there's only like this very small ball that can fit inside the set K.
But can you not like translate the set over in some way and like
Well,
move the
computing
origin?
translation is like, same as, if you want to compute the isotropic position, you do
Okay,
d to the 4. But that doesn't solve the asphericity problem because you can reintroduce this kappa through the reparameterization.
And then could you also maybe give some intuition as to why this kappa is appearing in like the algorithms that you're talking about?
Right. So essentially, how this reduction works is that you have a wrapper algorithm A that gets the gradients from the iterates that it played, but then what it feeds to the subroutine B is this modified gradients that can have a norm as large as like kappa. And so then when you apply the regressive algorithm B, usually like optimization algorithms scale with like the magnitude of the gradients. And so that's why you get the kappa. Yeah.
So I was thinking this somehow in your algorithms, like the standard basis is special. And I was wondering where it comes in. Is it like through this oracle, like you have the separation oracle, maybe that's somehow tied to the standard basis? Would that be possible to think of maybe a stronger oracle that can, you know, give a guarantee that's adapted to the you know, it works sort of in the same.
Yeah, so unfortunately the algorithm isn't preconditionally free. Like if you do Frank Wall, for example, it's independent of the parameterization because you're always computing the. So the downside of this type of separation-based algorithm is that it is kind of linked to the parameterization in a way. But we have a follow-up paper that kind of mitigates that to some extent. Yeah. Okay. And it's based on like ellipsoid method for OCO. I think Abhishek had.
I had a quick question. So maybe you mentioned this. Do we have lower bounds at all for direct reductions between the different types of oracles at all? Like in principle, you could have a reduction from separation oracle to a linear optimization that is not dependent on this, right? Is that ruled out?
So you can implement a linear optimization oracle using D calls to the separation, but then you also have some D cube or D4.
Oh, that does not depend on kappa, you're saying?
Only logarithmically.
I see, okay.
But you don't want to do D calls to an oracle per round. That's
but there are no lower bounds there, right? In principle, you could do that. Are there lower bounds there?
For like how to move from one to the other? I'm not sure, yeah.
Okay.
Yeah, all right.
Questions offline. Let's thank Zach again. Can the next speaker come up, please? Okay, great. Now we'll learn about alternating regret for online convex optimization.
Yeah, hello everyone. I'm Pingli, and today Sumita and I will talk about our work alternating regret for online convex optimization. And this is a joint work with Haipeng. He's here, and Mengxiao. In this work, we consider about online convex optimization, or short for OCO. At each round, the learner picks an action X from an action site X as a subset of the dimension space, and then the adversary picks a convex loss function, FT maps from X to R, and reveals it to the learner. And the standard goal is to minimize the regret defined by the cumulative loss of the learner and the best fix action in hindsight. And there are many interesting applications for OCO, and one of the most important application is learning in large games. And one example is like poker. And in zero-sum convex concave game, when both players apply OCO algorithms, classic result shows the time average strategies will converge to the Nash equilibrium. And since worst case regret for OCO is typically root T, so this means 1 over root T convergence rate to the Nash equilibrium. And based on this fact, many people work on accelerating 1 over root T convergence rate, for example, using optimism. And one of the simplest method is alternation, which means two players take turns to make decisions. And however, why alternation works so well have been a mystery until recent progress by Webisono et al. In 2022 and Katona et al. In 2024 and Sever et al. In 2023. They propose a key idea that it suffices to analyze alternating regret defined in this formula, which is the sum of standard regret and cheating regret. They show this alternating regret governs the convergence rate of alternating play in games. And let's focus on the second part, cheating regret, defined, which is highlighted in blue, defined by the sum of ft of xt plus 1 minus ft of u. And when the learner updates xt plus 1, the learner already has the information of ft. So this tells us cheating regret can be negative. And this gives us the intuition that alternating regret bound can be much better than root t even against an adversary. And in the recent work given by Savard et al. In the special case of online linear optimization, or short for OLO, they could achieve t to 1/3 alternating regret when x is simplex, and the order of log t bound when alternating regret when x is L2 bore. And since they focus on OLO problem, a key open question left from their work is that can we achieve little o root t alternating regret in general OCO and adversarial environments? And someone may wonder, could we use the standard reduction from OCO to OLO problem? For the standard regret by the convexity of the loss functions, we could have this inequality. And this inequality tells us it's sufficient to consider an OLO instance with linear loss where the loss vector is the gradient of the loss functions. However, when we apply the same trick to alternating regret, we would find the loss vector in the part of standard regret and the loss vector in the part of the cheating regret, which are highlighted in blue, are not the same. So this tells we cannot reduce the alternating regret of OCO problem to the alternating regret of an OLO instance. So go back to our questions, can we achieve a little o root t alternating regret in general OCO and adversarial environments? Our work affirmatively answers this question, and specifically, this work shows continuous hedge could achieve the alternating regret is of order d2 2/3, t2 1/3 for general OCO. And one may wonder why we care about this little root t regret bond, because this use T2 minus 2/3 convergence rate to Nash equilibrium and the cost correlated equilibrium in two-player convex concave zero-sum game and general sum game respectively via alternation. And we also develop another algorithm with improved time complexity or dimension dependence. One example is when x is an L2 bore. Alternating regret is of order 2 to 1/3 for quadratic losses, and note that there is no d dependency anymore. And finally, we show some algorithm-specific alternating regret lower bounds. And this is a simple introduction to our work. Next, Sumita will show more details about our algorithms and analysis.
Thank you, Ping, for the introduction. Now we'll see how to achieve order t to the 1/3 alternating regret for OCO and how we can apply it to games. So as a warm-up, let's consider the expert problem where the domain is the simplex and all the loss functions are linear. It is implicitly shown in Vivisono et al.'s work that in this setting, H can achieve an alternating regret of order t to the 1/3. So the key idea in the proof is to bound the alternating regret using the sum of these two terms, where the second term is what we call a KL commutator, and the KL commutator can be bounded by order eta cube using the third order smoothness of the convex conjugate of the negative entropy regularizer used in H. This gives us an alternating regret bound of order t to the 1/3. Now, in order to extend this idea to the OCO setting, we consider the continuous hedge algorithm. In this algorithm, at every round, the player plays the strategy xt, which is the expected value of x, drawn from the distribution pt, which is a generalization of the exponential weights update to a continuous set from a discrete set. So again, using the standard analysis, we can bound the alternating regret of continuous hedge by the sum of these two terms. Note that the first term is slightly different from the case of hedge, and the second term is similar to that of hedge, except that here PT is a distribution over a continuous set rather than a discrete set. So now we see that Vipisuno et al.'s proof to bound the KL commutator does not generalize directly to the OCO setting, but still we managed to bound it using order eta cube by directly analyzing the structure of continuous hedge update. I'd like to point out that the analysis is quite non-trivial and it deviates a lot from Vipisuno et al.'s proof, although I won't go into details of it. Again, choosing eta optimally gives us a regret bound of order t to the 1/3. Now we'll see how we formally define the alternating learning dynamics. So here we consider a two-player game with the convex loss functions u1 and u2 for the two players respectively. In an alternating play, the first player x receives a loss function u1 of yt minus 1 and updates its strategy to xt using the algorithm algx. Following this, the y player receives a loss function u2 of xt and updates its strategy to yt using algy. And this process repeats. So we show that if algx and algy are both continuous hedge, then we can achieve a t to the minus 2/3 convergence to the Nash equilibrium for a zero-sum game, and the same convergence rate to the coarse-correlated equilibrium for a general sum game. Although the implication for zero-sum games was already known in the Vipisuno et al.'s proof, the implication for general sum games is new. And I'd also like to point out that even though there exists faster convergence rates for simultaneous playing dynamics, our result is the first to show better than order 1 by root t convergence in case of alternating learning dynamics. Now we'll go to another algorithm which has a better efficiency or dimension dependence. So this is required because continuous hedge requires a log concave sampler, which is quite expensive, and its regret also depends on D for simple domains like the L2 ball. So in order to overcome this, we propose another simple algorithm, which is based on follow the regularized leader update. Notice that here we use the actual loss functions ft instead of the linearized losses, and the regularizer psi needs to satisfy certain constraints. For any general convex set X, we can always choose the entropic barrier to satisfy all these constraints. And we show that if X is an L2 ball, then FTRL with this particular regularizer can achieve this alternating regret for smooth Lipschitz and C self-concordant losses. When C is equal to 0 for the special case of linear and convex quadratic losses, we can get a regret bound of order t to the 1/3, which is completely independent of dimension dependence. In the interest of time, I'll skip the lower bounds, but we do provide some algorithm-specific lower bounds. In conclusion, our work shows that we can achieve order t to the 1/3 alternating regret for the OCO setting, and we also complement our positive results using some lower bounds. Our work does leave some open problems like what is the min-max optimal regret for OLO or OCO, and if we can extend the concept of alternation to more than 2 players. Thank you.
In the interest of time, we can take some questions offline to the coffee break. Let's thank the speaker again. And if the last speaker can come up.
Just 2 announcements before the coffee break. First, we still have some places for the dinner tonight. If you don't have registered, you can go to the welcome desk and ask for a place. Okay, so during the break. And the second announcement is concerning the social activities this afternoon. Okay, so please respect the starting time. Okay, people will not necessarily wait too long. Okay, so you have to be at the right time at the beginning. And in particular, for the treasure hunt, you have to be at 2:30 at the meeting point, which is indicated on your voucher. Okay, and so have a nice afternoon.
Yeah, there's one more talk.
Hello everyone, I'm Junfan Li from Harbin Institute of Technology, Shenzhen. In this work, we study the problem of unknown sparse linear regression. We propose a new polynomial algorithm which improves previous regret bounds under weaker conditions. Unknown sparse linear regression is the problem of unknown linear regression with limited access to attributes. There is a budget parameter k which is smaller than the dimension d. At each round, the learner can only observe k out of d attributes to make a prediction. There is also a relaxation of this problem. At the end of each round, the learner can observe some additional attributes. The size is k. The prime goal to solve the two problems is to develop efficient algorithm with no regret. The first one is the per round time complexity is polynomial to the time horizon t, the budget k, and the dimension d. The second goal is to provide a regret bound that is sublinear to t and is polynomial to d and k. However, it has been proved that without additional assumption, the two problems are NP-hard. Therefore, it is necessary to restrict the problem with some additional regularity assumptions. Previous work has established some mad assumptions, include such as realizable assumption, that is, there is a true parameter W star. The sparsity assumption, that is, the W star is K sparse, and independent identical distribution instance and linear independence of features. The compatibility condition requires that the covariance matrix, that is X times its transpose, is positive definite along directions in the restricted set omega S. Under different assumptions, there are two algorithms which enjoy per round time complexity in big OD and sublinear regret bounds. However, the regret bounds is suboptimal in terms of the dependence on D. It is D to the power of 8, and HW star, it is HW star to the power of 7. And there is also a factor, the square of K, in the first term. There are also polynomial algorithms for the relaxation of this problem. The regret bounds are still suboptimal to the dependence on T and D. In this paper, we propose a new algorithm for unknown sparse linear regression. Under weaker conditions, our algorithm improve previous regret bounds. The second term only depends on D to the power of 2 and HW star to the power of 2. And we remove the factor of the square root of K in the first term. Our assumption include realizable sparsity and compatibility conditions and the Gaussian noise. We further extend the algorithm to the relaxation of this problem. We also improve the previous regret bound under weaker conditions. Both our algorithms are polynomial time. Next, I discuss the lower bounds and upper bounds. There's still a lack of lower bounds on the estimation error and regret. The lower bounds on the estimation error is adopted from the result of sparse linear regression, which is a simpler problem than non-sparse linear regression. It can be found that there is only a small gap between the lower bound and the upper bound. The gap is the square of d. The lower bound on the regret is derived from the lower bound on the estimation error. There is a large gap between the lower bounds and the upper bounds. We conjecture that the lower bounds can be refined since the partial information in non-sparse linear regression. Next, I introduce the main ideas of the algorithm. Figure 1 gives an overview of the algorithm. The algorithm alternatively executes an exploration round and an exploitation epoch. At each exploration round, the algorithm uses density selector to compute a coarse estimate of the true parameter W star. During the exploitation epoch, we future fine-tune the estimate use unknown Newton step. There are some main techniques we propose or use. At each exploration round, we propose an algorithm-dependent sampling method and an adaptive parameter tuning scheme. Combine these two techniques with density selector, we can compute a coarse estimate hat WS. During the exploitation epoch, we use unknown Newton step to fine-tune the estimator, but more importantly, we propose a dynamic parameter initialization method. At each exploration round, we need to construct estimate on the design matrix and the corresponding covariance matrix. To this end, we use the estimate computed in the last exploration round, hat WS-1, to construct a sampling distribution. Then we use this problem-dependent sampling distribution to sample a feature from the instance. Then we uniform sampling another k-1 feature from the others without replacement. In this way, we can construct an estimate on the design matrix and the covariance matrix. Now we can use density selector to compute a coarse estimator hat WS by solving the following minimization problem with constraint, in which gamma S is a threshold, delta tau minus 1 is the estimation error. However, there is a technical challenge posed by the algorithm-dependent sampling scheme. That is, the threshold gamma S depends on the L1 norm of the estimation error, which depends on the true parameter W star. To address this issue, by rigorous analysis, we find that it is enough to provide a tight upper bound on the L1 norm of estimation error. Therefore, our solution is step 1. Assume that we have learned the true parameter W star. Then we can solve the problem and prove an ideal convergence rate. It can be found the convergence rate is independent of the true parameter W star. Then we can use the ideal convergence rate to construct an estimate of the threshold gamma S. Now we can prove that by this estimator, we can prove that the estimation error satisfies the following inequality. We can solve the inequality by an induction method to obtain the real convergence rate. Since the convergence rate is dependent on the number of exploration round, not the observed instance, therefore it is necessary to fine-tune the estimator. To this end, we first construct an estimator of the true support denoted by SS. Then we can solve an ordinary unknown linear regression on the observation. We use unknown Newton step to fine-tune the estimator, but incorporating a dynamic parameter initialization method. finally, I discussed two directions for future research. The first one is develop more efficient algorithm for online sparse linear regression, which can maintain the regret bound under the same assumptions. The second one is establish tight null bounds on both estimation error and regret. Thank you.
Does anyone have any really quick questions? Sorry, we're running a little bit late in the session. But if not, maybe we can thank the speaker again. And I was asked to reiterate that, yeah, if you're doing the treasure hunt, I guess it's 2:30 promptly, wherever it says on the sheets. So now, everyone, let's go and have some coffee.